Hello students, welcome to the classroom point. In today's session, we are going to discuss the two important reducing agents. They are lithium aluminium hydride and sodium boro hydride. Let us see their common points and common characteristics of both of these reducing agents. Both of these are the reducing agents. They reduce only polar multiple bonds. Polar multiple bonds means carbon double bond N, carbon triple bond N, carbon double bond O, nitrogen double bond O. So this type of the bonds are usually reduced by these reducing agents, and they do not affect the non-polar double bonds like C double bond C, C triple bond C, N double bond N. Second point is both of these reagents are nucleophilic reducing agents, means they reduce different functional groups by delivering H- ion and then proton is added from the solvent. So the question here is, whenever these reducing agents want to attack a particular functional group, they attack by the releasing of the H- ion. So H- ion is a negative particle, negative ion, so which is the nucleophile, so that they preferably attacks over the carbon, means positive charged atom in the multiple bonded functional group. So usually if you see any of these functional groups here, particularly if you see carbon double bond O, carbon gets the partial positive charge, oxygen gets the partial negative charge. So H- ion preferably attacks over the less electronegative atom of the multiple bond, usually carbon, so that the pi bond will be shifted over to the oxygen, and then protonation takes place from the solvent. In this sense, this whatever the higher electronegative atom is there, that gets the H plus ion from the either water or from the alcohol, that we shall see in the coming discussion. So whenever these reagents are releasing the H minus ion, H minus ion always attacks the carbon from the backside, means it actually approaches the carbon from the backside. So here the point is H minus ion always added to the carbon atom of the functional group, and H plus of the solvent is added to the heteroatom. Just now we discussed, that is other than carbon atom. Now you see these reducing agent structure, lithium aluminium hydride, sodium boro hydride. These are the structures of the both lithium aluminium hydride and sodium boro hydride. And between these two, lithium aluminium hydride is a strong reducing agent than the sodium boro hydride. Why? Because here aluminium hydrogen bond is so weak. Because aluminum is the metal and hydrogen is the non-metal, so metal non-metal bond is weak. And here boron is the non-metal and hydrogen also non-metal, so non-metal bond is bit stronger than the metal and non-metal bond. Each of these reagents can release 4 H minus, and you can see in this particular structure, aluminum is having the 4 hydrogens, similarly boron is also having the 4 hydrogens. So both of these reducing agents, each of these reducing agents are able to release how many H minus ions? 4 H minus ions. Hence, they can react with the 4 moles of the reactant, so that they can reduce the 4 moles of the compounds, and sometimes it depends on the type of the functional group also. So as I discussed earlier, H minus ion of these reagents always attack from the less hindered side of the carbon atom of the functional group. So they approach the functional group carbon atom from the back side, or wherever the less hindered side is there, means less crowded side is there, from that side they will attack. Now you see here different type of the reducing agents and their strength. Lithium aluminium hydride is the strongest reducing agent than the lithium boro hydride, which is stronger than the sodium boro hydride, which is stronger than the sodium cyano-boro hydride. Now, among these reducing agents, sodium boro hydride is a selective reducing agent and reduces only certain functional groups, that we shall see now. So when you come to these two reducing agents, lithium aluminium hydride and sodium boro hydride, lithium aluminium hydride reduces aldehydes, ketones, carboxylic acids, esters, acid chlorides, anhydrides, lactones, means cyclic esters, and epoxides to the alcohol. So all these functional groups will be reduced to the alcohol. And come to the point here, any alkyl halides are reduced to their respective alkanes, but tertiary alkyl halides are reduced to the alkanes by lithium aluminium hydride. We shall discuss sodium boro hydride later. First let me come to the lithium aluminium hydride. And if NO2 nitroalkanes are there, it gives the amines. So aromatic nitro compounds gives the azo compounds. If you take the nitrobenzene here you will get the azobenzene. And isocyanates gives the secondary amines. Amides will be converted to the primary amines. Secondary amines also will be converted to the secondary amines. Tertiary amides will be converted to these tertiary amines. So all nitrogen compounds you see here, whether it is a nitro compound or amide, whatever it may be, they are giving amines only, except aromatic nitro compounds. Now here hydroxyl amine will be converted to the again amine. Now if you take the cyanides gives the two different products in different temperatures. With the lithium aluminium hydride, if you use the less temperature, -degrees temperature, then it gives the aldehyde. But if you use the room temperature, RT means room temperature and pressure conditions, then you get the primary amine. But most of the textbooks they mention only RTP conditions, not this one. So if specifically they mention the temperature, then you will get the aldehyde. If they don't mention the any temperature, means you have to consider it as a room temperature condition. So automatically you have to write down the primary amine. So azides will be converted to the primary amines. And in this case, as I said in the first point, these reducing agents do not affect the non-polar multiple bonds. See here, if RCH double bond CH-CHO is there, if you use the lithium aluminium hydride, it reduces only CHO part to the CH2OH, and this double bond or triple bond will not get affected. But the same double bond, if it is connected to the benzene ring, then it gets affected. So it will be reduced. So here are CH2, CH2, CH2OH. So here I have written that isolated carbon-carbon double bond, triple bond, nitrogen-nitrogen double bond, ethers are not affected by both of these reagents. So these particular reagents and their characteristics and reactions, if you remember, then whatever the type of the molecule it may be, you will be able to answer the question. Now let us see about the sodium borohydride. And sodium borohydride is a very selective reducing agent. It reduces only a certain type of the functional groups. Aldehydes, ketones, and acid chlorides will be reduced to the alcohol. Rest of these functional groups are unaffected. Means carboxylic acids, esters, ethers, anhydrides, whatever it may be, they are completely unaffected by the sodium borohydride. Now, if you take the imines, they give the primary amines. Ozonides will give the alcohols, and actually I said just now that esters are not affected by pure sodium borohydride. But in addition to the sodium borohydride, if you use lithium chloride and diglyne, then this will function like a lithium aluminium hydride and giving their respective alcohols. Secondary and tertiary alkyl halides will give secondary and tertiary alkanes. Primary alkyl halides will not get reduced. You see, if you compare both lithium aluminum hydride and sodium borohydride, lithium aluminum hydride reduces both the primary and secondary alkyl halides to the alkanes, but not the tertiary alkyl halides. It converts the tertiary alkyl halides to the alkenes. But sodium borohydride do not react with the primary alkyl halides, only reduce the secondary and tertiary alkyl halides to the alkanes. Now, similarly, azides will give amines, and sodium tetrafluoroborate, benzene tetrafluoroborate, if you take benzene diazoam tetrafluoroborate, it gives the benzene. And here, just like in the earlier case, here we discussed, if any double bond is connected to the benzene ring, in the case of the lithium aluminum hydride, it reduces both the double bond as well as the functional group. But in the case of this one, sodium borohydride, whether it is conjugated double bond or not conjugated double bond, it will not affect these double bonded carbon atoms. It converts only CHO, means functional group to the it reduces their respect to other functional group. Now, when it comes to the lithium aluminum hydride reactions with a different respect to functional groups, among the functional groups of carbonyl compounds and different functional groups, the reactivity of the different functional groups towards the lithium aluminum hydride is in this order. Aldehydes reacts very fast with the lithium aluminum hydride than the ketone, next ester, next amide, next carboxylic acid. So there was one question, that which is the preferable method to convert the carboxylic acids to their respective alcohols, like this, using lithium aluminum hydride. Whether it is, means lithium aluminum hydride initially will be converted to the CHO, then to the CH2OH. Means I'm just giving the options only, or else converting this lithium carboxylic acid with react with the alcohol and giving the ester compound, and then lithium aluminum hydride, and finally giving the RCH2OH, or else direct reduction, which is the preferable method. The thing here is carboxylic acid is a compound that can easily release the H plus ion, and we are using the lithium aluminum hydride. This lithium aluminum hydride releases H minus ion. So H minus ion is a base, carboxylic acid is an acid which releases H plus ion. H plus ion combines with the H minus ion and produces the hydrogen gas. Means carboxylic acid will consume the lithium aluminum hydride, which is a costly reagent. So that to avoid this situation, lithium aluminum initially carboxylic acid will be treated with the alcohol so that we get the ester. Then this is reduced to the alcohol. Why? Because here also we have seen that esters are more reactive towards the lithium aluminum hydride than the carboxylic acid because of this reason. Because these two compounds are bit acidic in nature, so that they consume more of the lithium aluminum hydride, so that they are less reactive towards the lithium aluminum hydride. So that's why always you convert the carboxylic acids to the alcohols and then convert them to the first make this carboxylic acid react with the alcohols to form the esters, then convert these esters to the alcohols is the preferable method in the reduction of the alcohol carboxylic acids to the alcohols. Now, what type of the composition we have to use in the case of the reagents? So, composition of the reagents is lithium aluminum hydride dissolves in the ether and later protonated with the H2O or methanol or ethanol, whatever it may be. Here, lithium aluminum hydride is actually soluble in the ether, and we should not use the polar protic solvents. If you use any polar protic solvents, it reacts with the lithium aluminum hydride because it will H minus ion. So the reaction is so highly exothermic in nature, and even explosion also may take place. That is the reason why lithium aluminum hydride will not be subjected with the polar protic solvents. But in the case of the sodium borohydride, it is insoluble in the ether, so that we should not use ether combination of the sodium borohydride. We have to use the methyl alcohol or any polar protic solvents. So now let's see some example reaction, later application reactions. So in these example reactions, as we have seen that aldehydes, ketones, acid halides are reduced to their respective alcohols by using both of these reducing agents. But if you use the carboxylic acid, ester, anhydride, amide, any of these reagents, only lithium aluminum hydride can reduce these reagents to their respective alcohols and their respective compounds, but not by the sodium borohydride. Now let's see some important application reactions which were asked in the previous examination. So in this particular, this is the compound when it is subjected with the lithium aluminum hydride. As we said that lithium aluminum hydride do not react with the ethers. This point I had given here. You can see ethers are not affected by the both of these reagents. Okay. So when you take this compound subjected with the lithium aluminum hydride, only this particular ester area is affected with the lithium aluminum hydride, not with the ethers. Sorry. So these ethers are remain as it is, and this will be reduced to the alcohol part, and this is also alcohol part. Now you take one important reaction, that is cycloketone. So in this cyclohexanone, when you use the lithium aluminum hydride and sodium borohydride, we know that H minus ion comes from the both of these reagents. So H minus ion attacks over the carbonyl carbon, shift these pi electrons to the oxygen, so that oxygen gets the negative charge. Later this will be protonated with the solvent. Here solvent is the deuterium oxide, heavy water, so that D will be added to the oxygen. So we get this molecule. And if you use the lithium aluminum deuterate or sodium tetraborate in the presence of the water, D minus ion attacks over the carbonyl carbon, shifting these pi electrons to the oxygen, so that oxygen gets protonated with the again H2O molecule. So hydrogen will go to the high oxygen. So we get this molecule. That's why in discussion only I had given information that H minus ion of the reagents always will be connected to the carbonyl carbon or carbon, or else protonation happens to the only other than carbon atom. That means oxygen here. Now let us take another important example. So in this particular example, if you subject with this compound with both of these reagents, lithium aluminium hydride reduce both of these functional groups esters and keto group to the respective alcohols like this. But when you use the sodium borohydride, it will not affect the ester compound ester part, but affects only the keto part, so that this part is reduced to the alcohol and this is completely unaffected. So in this way you can protect one type of the functional group. So based on the type of the compound or product you want, you can use these reagents, any of these reagents. Now let's take one more molecule. So in this molecule, if we subject this molecule with the lithium aluminium hydride and sodium borohydride separately, lithium aluminium hydride can reduce ketones to the secondary alcohols, aldehydes to the primary alcohols, and amides to the amines. Whereas sodium borohydride do not react with the amides, only reacts with the both of these functional groups, so that secondary and primary alcohols are formed. Hence here amide part is unaffected by sodium borohydride. Now let us take this one, cyclic amide. Lithium aluminum hydride convert this double bond O part to the CH2. This all information was given initially. Now let us see some unusual examples, that is crotonaldehyde, where double bond is present. Lithium aluminum hydride do not reduce this double bond, affects only the CHO to the CH2OH. But if the same double bonded carbon is connected to the benzene ring, then this double bonded carbon also will be reduced to the respective saturated compound, and this CHO compound will be converted, CHO group will be converted to the CH2OH. So both are reduced here. Now let us take the ethyl acetate or acetic ester. When you use the lithium aluminum hydride, reduce keto group to the secondary alcohol, ester group, this particular part to the primary alcohol, and this will to the another alcohol. Now that is the cyclobutanol. This reaction is so fast. The reason here is the bond angle of this sp2 carbon must be 120 degrees, but actually it is bond angle is 90 degrees, so the molecule is unstable. But when you use the lithium aluminum hydride, it will convert the C double bond O part to the tetrahedral molecule, tetrahedral shape, so that OH will be formed, sp3 carbon atom, whose bond angle is 109.28 degrees. It means that 120 degrees bond angle is required. Now 109 is enough, so that the strain in the molecule is reduced, so that it becomes more stable now. And here crotonic acid, same lithium aluminum hydride, reduce only the carboxylic acids to the alcohol, and double bond is unaffected. If you use the aromatic ring here, not only benzene, even any aromatic compound if you use, then it gets affected. Now let us take the aldehyde, acetaldehyde with the hydroxylamine, so that oxime is formed. Oximes also will be reduced to the primary amines by lithium aluminum hydride. Now you take this cyanide, lithium aluminum hydride with different conditions. Lower temperature gives the aldehyde, higher temperature gives the amine. And epoxide, when is the epoxide? Here hydride ion, hydride part of the lithium aluminum hydride preferably attacks over this particular carbon, opens this ring. Why? Because it affects from this particular side only. Because this is the less hindered side, here methyl group is there, so that it cannot approach like this one. So this is the major compound. Now regarding the sodium borohydride reactions, you must remember one thing, that this is called the cyclic imide part. Whenever N or NH is placed between the two keto groups, it is called the imide, cyclic imide. Cyclic imides also will be reduced, means it will break one particular bond here, so that it becomes the alcohol and it becomes the CH2 and H2 primary amide. Similarly, if you take this molecule, this also will be reduced to the respective alcohol part, so this becomes alcohol and this becomes the amine. And you take the last one, aldehyde molecule, this primary amine, so that you will get the amines. Amines will be reduced to their respective secondary amines. Here the thing is, sodium Boro Hydride do not reduce the C triple bond N cyanide, but sodium Boro Hydride reduces C double bond N to their respective CH2 NH remaining group, like this. So hope you understand my explanation, and if you understand, please like this video. Thank you.